Last class, we have seen grammar representation for context-free languages, and we have seen a number of context-free grammars generating context-free languages. And the topic for today is the method of proving correctness of a grammar design. So, how we can prove the correctness of a context-free grammar? We will try to understand the proof technique, which is basically the principle of mathematical induction, by using an example which is sufficient to illustrate the use of the proof technique. So consider the example. The language is the set of all strings over AB with equal number of A's and B's. So I am giving the name capital A as the name of the language, and you want this grammar G with 4 productions. This is the same grammar that we discussed in the previous class, and the question is, how can we prove that the language represented by G with these 4 productions is precisely this set of strings? And the proof involves 2 different steps. First is proving soundness. And what is soundness? If W is a string derived from the start symbol of the grammar G, that is, W can be derived using 0 or more steps from the start symbol, then W must contain equal number of A's and B's. So soundness says, if something is derived using the grammar, then that is in the language. That is soundness. The other part is completeness, which says, if W is a terminal string with equal number of A's and B's, then W can be derived from the start symbol of G. That is, W when containing equal number of A's and B's, then any such W can be derived from the start symbol using 0 or more steps. And we can use principle of mathematical induction to prove both soundness and completeness. Try to understand how can we do this using this example. Let us start with the claim for soundness. This is the example grammar. Soundness means we have this claim: if alpha is a sentential form, recall that a sentential form is nothing but a string of terminals and non-terminals which is derived from the start symbol of G. And here the claim is that if alpha is derived from the start symbol of the grammar using n steps in the derivation, then the number of A's in alpha must be same as number of B's in alpha. That is, if alpha is derived from the start symbol using n steps in the derivation, then alpha must contain equal number of A's and B's. Thus, we are going to apply induction on the number of steps in the derivation. And not that here we are proving it for any alpha which is a string of terminals and non-terminals. It's enough if we can prove it for string of terminals, but we are going to prove it for even a stronger case, which is enough for proving the soundness. And this will help us in the proof. And so the induction is on the number of steps. For the induction base, see what happens when the number of steps is 0. When the number of steps is 0, you have not applied any production, so what you derived is the start symbol only. So alpha is what is derived, which is same as the start symbol because nothing is applied. In this case we are done because the number of A's in S is 0, which is same as number of B's because no A's and B's, only S. And now the induction step. You consider when the number of steps is k plus 1. So how will the Derivation look like from the start simple by applying k number of productions or by applying k steps, you derived a string of terminals and non-terminals, and then you applied one more step, and finally you derived alpha. That is, alpha is derived in k plus 1 steps. Now maybe you can ask, why is this form assumed? It's because in order to apply one more step, I must have the capital S in it. And before or after capital S, I can have anything including epsilon. And beta and gamma are arbitrary strings. So this is a fair assumption of the structure of the string. Only if capital S is there, I can apply any of these productions. So that's fair. Now there are 4 cases depending on which production you apply from this string. Case number 1 for applying the production number 1. That means you are applying this production. So here capital S is replaced with the RHS of this production. What is it? Small a, capital S, small b. So exactly we are replacing capital S with the RHS of this to obtain this string. Now you look at the number of A's in alpha. We want to prove that it is same as the number of B's. But what is it? Alpha is this string. So number of A's in this string. I can write this as the number of A's in this string plus 1. Why? Because how you obtained this alpha from this string? Replacing capital S with a small a, capital S, small b. So the number of A's in addition you are getting is only 1, this a. And that is why I say this is number of A's in this string plus 1. Now from the induction hypothesis, I know that these two are equal. Why? Because we derived this string in k steps from capital S. So from the hypothesis we know that if we derive any string in k steps, then in that string the number of A's must be equal to number of B's. So these two are same. So if it is k, this also is k. So this is correct. Now I can say that I can rewrite this quantity is same as this. Why? Because now suppose that the number of B's in beta S gamma is k, some value of k. Then what will be the number of B's here? What I did is I have replaced capital S with a small a, capital S, small b. So I added one more b. So if it is k plus 1, here itself it is k plus 1. So these two quantities are same. And what is this? You look at this. This is exactly alpha. So we proved that this is number of b in alpha. This is exactly what we wanted to prove. So case 1 is done. Now see for case 2 where we are applying this production. This is a very similar proof. The only difference is that rather than replacing capital S with small a s b, we are replacing it v s a. That's the only difference. Proof is very similar. This is the number of A's in alpha. We can say that it is nothing but the number of A's here plus 1. And from the hypothesis we have these two quantities same. And now if you rewrite this, you can get it as, okay, I am replacing capital S with this thing. Okay, then what I will get? I will add one more b here. So this one is going, and that's getting here itself because of this v. So this is a very similar proof. So we are establishing that the number of b's in alpha is same as number of a's in alpha, and we need to prove it for 2 more cases. Now for case 3, that is when we replace capital S with SS, this is exactly what we are getting. So what is the number of A's in alpha? You can see that it's exactly same as number of A's here, because the only difference is the presence of capital S where there is no A. So this is exactly same as this. And now from the induction hypothesis we know that number of A's here is same as number of B's, because this is derived using k steps. Now I can say that doesn't matter if I just put a capital S here, because in capital S no B is added. So what is exactly this is exactly number of B's in alpha. So it's done in that case as well. Moving on to the last case, when we apply production number 4, so you are replacing capital S with epsilon, you are getting this. What's the number of A's in alpha? You can say that it's same as here, because the capital S is not containing any A. Now from the induction hypothesis, we know that this quantity is same as number of B's here. And you can safely take out S because there is no B in S. So you are getting number of B's in beta, gamma, which is exactly alpha. So we are done. So in all the 4 cases in the induction step, we prove that the string which is derived is containing equal number of A's and B's, and hence proved. So we prove that if a string of terminals and non-terminals is derived from the start symbol of the grammar, then the derived string contains equal number of A's and B's. And this applies for a string of terminals also. And hence the soundness claim is proved. Now it remains us to prove the completeness claim. And for this particular grammar, the completeness proof is a tough one. So for that, we will be proving a subclaim about a string in the language before we go for proving the completeness claim. And here is the subclaim which claims that if W is a string in the language, that means if W contains equal number of A's and B's, then W must satisfy one of these 3 conditions. First condition is W can be split as XY, such that both X and Y contain equal number of A's and B's. That is, number of A's in X is same as number of B's in X, and similar case for Y as well. So either you can split W into 2 strings X, Y such that both X and Y are satisfying the same condition. If this is not the case, then W either starts with A and ends with B, or starts with B and ends with A. It's not very clear why is it so, but we are going to prove it using a lemma. And the lemma says, suppose W is not satisfying the first condition, that is W is in the language, that means W containing equal number of A's and B's, but we cannot split it into 2 strings X and Y such that each of them is also satisfying the condition. Then we can claim that W cannot start and end with the same symbol. That is, if W cannot be split into XY, satisfying these 2, then W cannot start and end with the same symbol. And we need to prove it. We can prove it by applying the method of contradiction. For the purpose of contradiction, assume that W starts and ends with the same symbol. For example, suppose W starts with A and ends with A, and you call the middle string as Z. So how will W look like? Like this. It starts with A, ends with A, and the middle string is Z. And now at point n minus 1, n is now the number of symbols in W, and here to this point the number of symbols is 1, here it is 0, here it is 2, likewise it goes, this is n minus 1, and here is n. So at n minus 1 till this point, all these symbols if you look at, so what is the string? AZ is the string. So what will be the number of B's in AZ? We can see that this must be 1 more than the number of A's, because in the whole string we have number of A's and B's are same, and there is 1 A left with. So in this part the number of A's must be 1 less. So this is exactly what we can see. Number of B's is 1 more than the number of A's. That is the point. That is why when we are counting that A also, number of A's and B's are becoming the same number. So you can rewrite it as number of B's is more than number of A's. Now suppose you move to an arbitrary point here, say ith point. What will be the relationship between the number of B's and number of A's? So what is your guess? Is it greater than or less than or same? We can prove that it is greater than, it must be greater than. Why? Because suppose it is same, both A and B are same at this point. That means here the number of A's and B's are same. Then you can divide it into two strings at this point. Call this as X and this as Y. Now because in X you have equal number of A's and B's, in Y also you must have equal number of A's and B's, because in the whole string the number of A's and number of B's match. So it cannot be same. At this point cannot be same. Now the only other question is, because we are assuming that W cannot be split into X and Y. But if at this point the number of A is equal to number of B's, you can split. So it cannot be same. Then can it be less than? That is, the number of B's less than number of A's? No, you cannot have it, because you know that at this point it was greater. Then at this point to be less than, there must be a point in between at which number of A's and B's are same. That cannot be true. Then at that point you can divide it into X and Y. So it can never happen. Now here is the point that gives you the solution to this. Now we proved that at any point this is the case. Number of A's at that point is greater than number of B's. And at this point the string is just A. It is number of B's in A is greater than number of A's in A. That is a contradiction, because this is 0. Number of B's in A is 0 and number of A's in A is 1. This is a contradiction. So in fact actually to satisfy this, the number of B's must be 1 more than the number of A's. So this must be B. That is the only case you can satisfy this condition. So the first simple must be a B. Hope you followed it, otherwise watch it again and see what is going on. So we proved that if it ends with A, then it must start with a B when it is not satisfying the first condition. A very similar proof applies when it starts and ends with B. In this case, it starts and ends with B, and you can establish that the first simple is A. And hence the lemma is proved. If the lemma is proved, the proof of the subclaim follows, because the lemma proves that if W does not satisfy condition 1, then W cannot start and end with the same simple. So W must satisfy either condition 2 or 3. So we proved the subclaim, and hence for any string W in the language, W must satisfy any of these 3 conditions. And this is now enough for us to move forward and prove the completeness part of the correctness. And here is the completeness claim. If W is a string of terminals, that is sentence, containing equal number of A's and B's, then W can be derived from the start symbol of G. And here we are applying the number of A's in W, which is same as the number of B's in W. See, in the previous case, for soundness, we were using number of steps in the derivation. But here we are using the number of A's in W, which is same as number of B's in W. If there are n number of A's and B's in W, for any natural number n, then we are going to prove that W can be derived. And base case, when the number of A's in W is 0, which is same as number of B's, then W must be epsilon. Number of A's in W is 0, number of B's in W is 0. And this is done because we can derive epsilon from the start simple in one step if you apply product number 4. So you can derive when W is epsilon, when n equal to 0. And here we are using strong induction. Strong induction is different than the ordinary induction, and the difference is in the case of induction hypothesis. Here we will have a strong induction hypothesis, and here is the strong induction hypothesis. If W is a string with equal number of A's and B's, and number of A's, which is same as number of B's, is less than or equal to K, then W can be derived from the start simple of G. That is the strong induction hypothesis. Strong means in the normal case we are assuming it only for K, but here we are applying it for all values less than or equal to K, and that is strong induction. Normal induction means assume it for K and prove it for K plus 1. Strong induction means assume it for all values less than or equal to K and then prove it for K plus 1. That's it. So here we are assuming that if the number of A's, which is same as number of B's, is less than or equal to K in W, then W can be derived. Any such string can be derived. That is the induction hypothesis, strong induction hypothesis. And this is enough. Now the proof is not at all difficult. We will be applying the previous subclaim. Case number 1 in the induction step, when the number of A's, which is same as number of B's, is equal to K plus 1. First case, that is W is in the language, hence W can be split into X, Y, so that both X and Y will contain equal number of A's and B's. In this case, I will do this. From the start simple, I apply question number 3. What do I get? Capital SS. Then I claim that the first capital S can be replaced with small x. Why? The only thing I know is that X is containing equal number of A's and B's. Now from the induction hypothesis, I know that the length of X is strictly less than K, less than or equal to K, because W is written as XY. And from this condition we know that X containing equal number of A's and B's. That is, X is a string whose length is less than or equal to K and containing equal number of A's and B's. Then from the strong hypothesis we can have this. Okay. And the same argument works now here. This capital S can be replaced with Y. In 0 or more steps I can derive Y from capital S, because here we know that number of A's in Y is same as number of B's in Y, and also the length of Y is less than or equal to K, because length of W is K and W is nothing but concatenation of XY. So this is the case and hence proved. So you can derive it. For the case 1 you can derive it. If W is satisfying case 1, then you can derive. Then case 2, that is if W satisfies this condition, starting with A and ending with B, then I shall first apply plus number 1. I am getting this, no doubt. Then I will claim that now I can derive Z from S using 0 or more steps. Why is it so? Because I know that in W there are equal number of A's and B's, and to obtain Z from W, what I did is I just took out one A and one B. So number of A's is decreased by 1 and number of B's is decreased by 1, and hence the number of A's and B's must be same in Z as well, because from W how are you obtaining Z? Remove one A, remove one B, so same number of A's and B's are removed. So this is the case. Now the length of Z is what? Number of A's in Z is 1 less than the number of A's in W. That is, at least it can be at most K. So it is less than or equal to K. So from the induction hypothesis, strong induction hypothesis, we know that S can derive Z because Z is containing same number of A's and B's, and the number of A's in Z is less than or equal to K. Note that here we need to apply strong induction, and hence proved in this case as well. And the last case, when W starts with P and ends with A. Very similar proof. Here the only difference is here. Apply question number 2. Then a very similar argument can be used to establish that I can replace capital S with small z, because Z is containing equal number of A's and B's, and Z is containing number of A's less than or equal to K because of this, and hence proved. So from the subclaim we know that if W is a string in the language, then W must satisfy one of the 3 conditions, and for each of the 3 conditions we proved that W is derived. So from the subclaim it follows that if W is a string in the language, then W can be derived from the start simple using 0 or more steps. And with this we are finishing this proof, and I am giving you a practice question for you to understand what exactly is happening. Prove that this language is generated by this grammar. So you have to prove that the language of this grammar is precisely this language. So in this class, we have seen how the principle of mathematical induction can be used to prove the correctness of a grammar design. You can use it for any kind of grammar, and there are 2 parts, soundness and completeness. And soundness means if a string is derived from the start symbol of the grammar, then the string is in the required language. So the derivation is sound. You derive only a required string. Completeness means if you take an arbitrary string in the language, then that string can be derived from the start symbol. That means the grammar is able to derive any string in the language. That is completeness. Soundness means grammar can derive strings only in the language. And applying induction here is not very easy in all the case. What we discussed as an example today is one of the toughest example for proving correctness, and what is given as exercise is one of the simplest one. So please try proving the correctness using induction and see how you can use induction or strong induction to prove the correctness of a grammar design. Thank you.